just going to walk you through how to rotate a shape around a line to make sure you understand what's going on. Okay, basic idea though, let's discuss. You need to know that the volume of a cylinder is pi r squared h, right? So everybody knows that. All right, and typically, we see cylinders that look like this, right, where this is the height and this is the radius. But if you turn that on its side, you'd have a cylinder like this, where that's the height and that's the radius. Okay? And what we're going to do here, ready, is we're going to take this idea and we're going to crush that down so that we have a cylinder that's actually just a super infinitely thin slice of a circle. Kind of like a sheet of paper. Think of that, like a super thin sheet of paper that really has a thickness to it, right? So, if we have two functions. Let me draw that a little better. Let's actually name the functions, I guess it'll be easier for us. Let's say we have f of x here, which is the square root of x. All right. And let's take g of x here, which I'm going to say g is 1/2 x squared. All right. So we need to know their intersections, right? We need to know where they're going to hit. This is definitely 0, 0. This point here, I could use a calculator to solve it, right? I could set them equal to each other and solve by hand if I had to. But for right now, just to keep things simple, I'm going to call this point up here just A, B. Okay? And again, we could, you set them equal, solve it, or you can use a calculator and find that intersection, right? But let's keep it simple, let's call it AB, whatever those values happen to be. Now, when you use a calculator to do that, though, you have to write those numbers out all the way. So I'll show you that in a second. But here are the main concepts of what we're doing right now. The area of that shape, we're filling it with all these little rectangles, right? We're slicing it up and we're filling it with all these little rectangles and we're adding up all the rectangles, okay? And that's going to be the area of the whole shape. But each rectangle has a thickness of dx and a height like that. So the area of a rectangle is always just the base times the height. I'm going to write it as height times base because that's how we usually see it with integrals, okay? Well, the base of each one of those, let me write that a little bigger. Right? The base of each one is going to be dx. Okay, that's its width, right? Height times width, really, I guess, if you're thinking like that. And the height of each one, the height, think about a number line that look like this, okay? If you're ever confused about what to do. If this number up here were 12 and this number down here were, I don't know, 4, and I said, how far apart are these? You're going to tell me 8, because you're doing top minus bottom, 12 minus 4, right? Well, what's happening with my rectangles is they're all changing, right? When I get close to the edge here, my rectangles are going to be really thin. Out in the middle, they're going to be the biggest they can be. And down here, they're going to be thin again. But for any specific x value, the top of that rectangle, in this case, is root x, and the bottom of the rectangle is 1/2 x squared, f minus g. Okay? So one rectangle, let's just move this over some so this all fits. So the base is just dx. But the height is actually f of x minus g of x. But that's the area of one of them. We want to add them all up. So the area is really, the area of that shape is the integral of f of x minus g of x. And you can just drop in what functions those are, right? Times the thickness of each rectangle. And you're going to go from 0 to a. That's it. Okay? Makes sense. Yep. Okay. Now, we also have this notion of volume. Now, volume is a three-dimensional concept, right? So when you have a two-dimensional graph, that doesn't have a volume itself, all right? But we can use a two-dimensional area to create a three-dimensional shape, okay? And we do that two ways in the Calc AB class. The first is we take that shape and we rotate it around a line, which seems kind of weird, but you guys ever see those bell decorations? They kind of look like this, sort of, and you can like rotate them out. And they make like a big three-dimensional bell-looking thing. That's a terrible drawing of that. But they make it for like holidays. Like they kind of fold flat. You can rotate them out. I guess if that makes any sense at all. But you can also imagine like if I took, let me see here, a square, and I rotated it around like this point right here. like that, it would make a cylinder. That's what it will make. You rotate it around. All right? So it doesn't matter what shape it makes. It's going to make a big circular looking thing. So if I were to rotate this shape, so I'm going to erase all this junk here, just so we can see this thing. If I was to rotate this shape around a line, now the line could be vertical or it could be horizontal. All right, so let's say we're going to rotate around the line. I'm going to pick down here, y equals -6. And the question will say that, right? What's the volume of the shape created when this region is rotated around y equals -6? All right, I'll tell you all that junk. So, can you imagine? Let me switch up colors here. Boom. Okay. What you're really doing here, and this is always my advice to you, okay, to do a rotation, put your pencil on the axis you're rotating around. So I'm going to put it right there where that point is on -6. And you draw out to the shape you're rotating, always perpendicular to your axis, okay? So I'm going to draw a line that goes like this. Okay? That's what I'm rotating, that line right there. And you'll notice, no matter where I put my pencil on this, the outside of this shape is always going to be f of x. Okay? That's called the big radius, big R. So when I rotate this thing around, again, it's going to be kind of weird. You can imagine it's going to look kind of like a bowl with like a hole down to the center of it, right? So this is going to rotate around like this in a big circle. But we're rotating the entire shape. But I'm just looking at one individual one. And I say this in my other video. You're thinking about this as like a slice of like one card of a deck. All right? The volume of that shape, it's a volume now because that's three-dimensional, is pi r squared times height. But the height is this infinitely thin slice and change in x. So height just becomes dx. The pi is just kind of chilling. It's not doing anything, right? And the radius is the distance from the center to the outside. Okay? And it doesn't matter that we're calling it a radius. All it is a length. It's just the top minus the bottom. Now you'll notice when we did the area of that blue shape, it was f minus g, right? It was all inside the shape because it was the area. If you're rotating around something, it's not going to be f minus g. In this case, it's f minus -6, which seems weird. So it's really minus -6, but it's really +6 squared. Okay, and you can definitely simplify that to +6, right? That's what that equals. That's fine. All right, that's the volume of one of those disks. I want to add all the disks together. Okay, that's what the integral does. It adds up infinitely many things, but I got to tell it from where to where. So this is going to be from 0 to a. Okay, now that's not our final answer because that's just the outside shape rotated around, right? That's going to create a big solid, like weird, like circular shape. Okay, we want, for whatever reason in particular, to rotate this little blue shape around. So there's actually going to be a little hole in the center. Kind of like this. Well, terrible drawing there, but you can imagine that, right? There's going to be a hole in the center. It's going to be, a circle, but boom. Right? So we need to subtract off that volume. Like that volume's not there. So when you find the area of a circle with a hole in it, right, you find the area of the big circle minus area of the little circle. Okay? That's what we're going to do here. We need to subtract off the volume of that little thing. So it's minus. It's still going to be pi r squared h, though. It's just a cylinder that we cut out. So it's pi integral. But r now, so let's zoom in on that shape again. You don't need to draw it like this, okay? Here's how you can find what they are. Draw to the outside. Do a quick check on the whole shape. Make sure you're always hitting the same curve. That's big R. And then do the same thing. Put your pencil back on there and draw it to the first time you hit it. Do it a couple times. Doesn't matter where I draw this. The first time I hit it will always be g of x. So that little radius that I'm actually subtracting off is g minus -6. Top minus bottom. So we're going to subtract off g of x minus -6, but that's just +6. Right? And still from 0 to a. And because they both have the same bounds, which they always will for us, okay? I mean, it could get a little weird. I guess we could have a weird bottom shape or something. So if the top curve ever changes or the bottom curve ever changes, you need a new integral because your definition of what big R and little r is going to be different. You don't see that a lot. There's really no reason for it to happen in a question except to make it look a little more complicated. All right? But you can put these together. So this would be f of x plus 6. And you can plug in what f is. That's a g. F of x plus 6 squared minus g of x plus 6 squared dx. All right, and you would drop that into a calculator. If they don't want you to use a calculator, like f and g will be simple functions, and it'll be something you can square out kind of easily. All right, everybody okay with that? I'm going to make a small change and show you how this affects. So that's when the line's below it, right? It doesn't matter where the line is, just draw a picture of it. You're always doing top minus bottom in this case. So let's say I want to rotate around the line for whatever reason. Again, just changing it up. The line that was up here, y equals like 10. All right, I'm going to do the same thing I just did. I'm going to put my pencil on the axis that I'm rotating around, draw to the outside of the shape. It does not matter which function's on top of the actual region we're looking at. It doesn't matter that root x is the top function. What matters is which one's further away from what we're rotating about. Okay? So big R in this case, you ready? This is how this would change. I'm going to erase this. Big R in this case would actually be that line, which is 10 minus g of x. But we're still rotating around, we're still using dx, right? And we're still going from 0 to a. That's what x is doing. Then, little r, same thing. Put your pencil on the axis, draw to the inside. Check that it's the same everywhere. Okay? You're going to get 10 minus f of x. Questions? I'm going to show you how to go around a vertical line real quick too. It's similar to an area, like horizontally. You got to use y's. Okay? So, questions out there? I'm going to erase this. Okay. So let's say we want to take this same exact region, right? So this point is still AB. The same exact region where this is f, which is root x, and this is g, which is 1/2 x squared. But now I want to rotate it around a vertical line, which is x equals, I'm making this up, I don't know, we can use 10 again. Okay? So keep in mind, gang, a vertical line is always x equals, but the y-axis is vertical. It seems like weird because they switch, but it's really x equals 0 is the y-axis. All right? So the y-axis would also be a vertical line. Don't let that confuse you. Okay? But you were going to do, if you follow Mr. Smith's steps to finding how to rotate, get the correct integral, put your pencil on the axis you're rotating around. There it is. Draw perpendicular to that, to the outside of the shape. That is big R. Okay? A rotation will always be pi r squared h, because it always creates a cylinder. The other shapes, like the other kind of volumes that we talk about, could have any kind of crazy shape. But a rotation always makes a circle. Okay? So it's always pi r squared h. So think about a number line. If we had a number line and 10 were here and 2 were here, and I said, how far apart are they? You would say 8, 10 minus 2, right minus left, right? The bigger value minus a smaller value. So in this case, we're really subtracting x values, right? This is an x value right here. Cool. Big R is 10 minus, now we got to talk about this. It's not f of x. It looks like it should be f of x, right? Because that's what it's hitting. And it is that curve, but we can't call it f of x because right now what I'm really doing is taking this little tiny rectangle and I'm rotating around in a big circle. So the height of my cylinder is no longer dx. It's now dy because I'm crushing y down. So I'm going to have a dy at the end of this thing. Well, what that means is I can't have 10 minus something with x's in it. I have to have y's. So all we're going to do is take that curve, however it's defined, and solve for x. It turns out x is just y squared. That's what we have to use. It's the same curve, but we need it defined as an x equals. Okay? So it's 10 minus y squared. And then my little radius, again, pencil on the axis, draw to the first time you hit the shape. No matter where I do this, look what I hit first. Always g. So little is 10 minus g, but it can't be g of x. It has to be, we got to find what it is. So if y equals 1/2 x squared, we're going to multiply it by 2 and take the square root, right? You're going to get 2y equals x squared. You're going to take the square root. Now, when you do that, you're technically going to get plus or minus on there, right? Because you're taking the square root of some stuff. But you can see all these x values are positives. You all see that? Like every single one of these x values on this curve is positive. Like this parabola has another side over here. If I was hitting that side, it'd be the negative version of the square root because all the x values are negative. All right, but we don't get too crazy with that. So it's 10 minus the square root of 2y squared. Keep in mind, 10 minus root 2y squared is not 100 minus 2y. It doesn't square like that. You got to FOIL it out. But you don't need to worry about that. You're going to have a calculator for this kind of question. All right? But now we're integrating from 0 to what y, so y starts at 0 right here, but it goes up to b. Everybody okay? And then last but not least, if we had to go around a line that was back here, it'd still be y's, but now big R, so here, you guys can try this out. Let's say this was x equals 5, negative 5. Okay, oh, I forgot I'm making a video. I can't give you time to try it out. Oh wait, yes I can. I'm so good at this. Tell if I'm paused or not. Is this paused? Okay. So if you're watching the video, hopefully you pause it and try this out. But if not, I'm going to show you how to do it. Ready? You should have gotten pi. It's going to be the integral from 0 to b because that's what y is doing. Big R is going to be g, but you got to solve for it, which we already did. So it's root 2y minus negative 5. Boom, minus. So it's big R squared, minus little r squared. So that's going to be f, which we said was y squared minus negative 5 squared dy. Any questions? Good? Yeah. Okay. And then the last kind of volume you're going to see is like if it's the base of a solid. So let me draw that shape again. Again, root x, 1/2 x squared. We call this point out here a to b. Cool. This is root x. This is 1/2 x squared. So they might say this is the shape of some solid, right? So they'll write it like this. The region between square root x and 1/2 x squared, whatever, okay, just because I'm typing it, is the base of a solid. That means it's the bottom of a shape. It's the footprint of a shape. Now, yeah, cool. So, just because you know what the bottom of a shape looks like doesn't mean you know what the shape looks like. You just know what the bottom looks like, right? So a cylinder's bottom would be like a circle, right? But it's possible that cylinder goes up and has like a weird point, like a cone or something. Like the base would still be a circle, okay? So, but it's the base of a solid, and what they're going to tell you is the cross sections, which are like the slices of it, are all the same shape of some kind, defined by the bottom of the shape. So they might say this. Find the volume of the shape if the cross sections are, and they'll give you a couple. I'll do a few of them and show you what's going on, okay? So first off, they got to tell you how they're slicing it. Either perpendicular to the x-axis or perpendicular to the y-axis, right? Are they slicing it up and down or left and right? Cool. So that's going to change whether we're using x slices or y slices. Okay? Perpendicular to the x-axis that are, I don't know, squares. Cool. But they'll also give us perpendicular to the x-axis that are semicircles. Cool. They can give us any shape they want as long as we can find the area of it. Perpendicular to the y-axis that are equilateral triangles. And we'll do one more just for fun. Perpendicular to the y-axis that are, you ready? This is a good one. Isosceles, how do you spell this? Least triangles with a leg in the plane. We'll talk about that in a second, okay? So, here's what that means. So imagine me taking that shape and kind of turning the axis like three-dimensional, okay? So imagine I took the axis, turned it 3D a little bit, right? Tilted it. So we have root x coming out like this. We have g of x coming out like this. And we're kind of like up in the corner looking down on it. What's that called? What's that view called in video games? It's not third person, it's 3D. It's got a name when you look at it like that. It doesn't really matter. Okay, but so I'm taking this slice right here. We're going to do the first question, number 1, right? It says perpendicular to the x-axis, that's a slice, sticking out of the board. So here's that slice right here that I'm looking at. Sticking out of the board is a square. I should draw this in blue. Let's make this better for us. We have the technology. So let's draw it up here, actually, it's a little bit smaller. So perpendicular to the x-axis, sticking out of the board is a square. Cool? And wherever you draw that, wherever you cut the x-axis, let me try and draw this correctly. Wherever you cut the x-axis is the square, sticking up like that. You can imagine what the shape would look like, right? There's another one right here. That should be a square, it is, okay? So there's little ones here, right? That'd be a little tiny square. Boom, there's little ones down here. But it makes some shape, right? It'll look kind of like a weird cake or something, I don't know. All right? Probably not a cake. But anyway, the volume of it is just the volume of each little slice added up, just like it was with the circles. That's what an integral does, okay? But since they're all like squares, if the area of a shape that's the same, like a cylinder, right, on top and bottom, is just area of the face times how thick it is. Well, each one of these has a thickness of dx. And the face is just the bottom times the bottom, right? It's a square, right? Whatever the bottom happens to be. So the area of one of them is just the base times dx. Okay, that's all that's happening. Base times dx. That's one of them. We need to integrate all of them to add them up. So we can go from 0 to a. So the only question is, well, what's the base? Well, the base is always going to be, look, no matter where you draw it, the distance between these curves. So top minus bottom. So number 1 is just the integral from 0 to a of f minus g squared dx. That's all it is. Okay? For the second question, now they're not going to be, I'm going to get rid of you. Okay. Okay. Well, this is closing here, but now they're not going to be squares, they'll be semicircles. Same idea. So now from here to here, there's like a semicircle sticking out of the board like that. And there's a semicircle sticking out of the board like that. And there's a semicircle sticking out of the board like that. And there's a little semicircle here, okay? Easy enough? So all we got to do is, again, find the area of the face times its thickness. So this is still going to be a dx, right, times its thickness. We just need the area of the base. And what happens is this, like the base is, not the base, of the face. So the area of a semicircle, everybody knows this, is 1/2 pi r squared, right? But r is actually like this distance, it's half of the base. So it's actually pi, or 1/2 pi times half of that base squared. That's what the radius really is. And if you simplify that out, it just becomes this. It's b squared, right? But you got the pi and you get a 4 underneath here times another 2 is an 8. Okay? So semicircles, and this is just a formula you can memorize. If the base is like whatever the base happens to be and their cross sections are semicircles, it's just pi over 8 base squared. So the answer to 2 is just like the answer to 1, except you put a pi over 8 up front. Okay? For question 3, changes up. Now we're perpendicular to the y-axis. So can you imagine this? Now our slices are running this way. They're still sticking straight up out of the board, but now they look like this. Well, that's an infinitely small change in y. Okay, so now I gotta use dy. But the base is still from here to here, curve to curve. Okay, so it looks like it should be g, which I didn't even call g, I called it y, but g minus f. But because we're using dy, we've got to solve these. So this is really x equals square root 2y. That's what that, same as that curve. And this is really x equals y squared. All right? So again, this is not really drawn appropriately for me to do this, so I'm trying my best. So this is the shape we're looking at right here, right? And there's a triangle sticking out of it. Like that. Okay? And it turns out, if you don't know this, the area of an equilateral triangle is root 3 over 4 times the bottom squared. That comes from trigonometry. That's root 3 over 2 popping up from sine of 60 is root 3 over 2. That's where it's coming from. It's not magic. It just, I can show it to you, but just that's the area of an equilateral triangle. So the volume of this shape is just root 3 over 4, the base squared dy. But we're going from 0 to b now. right? Because the y value of that point up there is b. We're going from 0 to b. So this would be root 3 over 4, the integral from 0 to b of the right side, which is root 2y, minus the left side, which is y squared dy. All right? And if instead of them being equilateral triangles, like for question 4, they were isosceles, oh, let's just say right triangles. Isosceles right triangles with a leg in the plane. You guys know what an isosceles right triangle looks like? It's a 45, 45, 90. That's all that is. It's that. Okay? So we're saying the leg right here is in the plane. So this would like stick up like this and like go like this. This is like a terrible drawing, but something like that. This would be a right angle. Okay? But look, this side here and this side here are both the same. It's isosceles. So the area of that triangle isn't root 3 over 4 base squared. It's 1/2 base times base. It's just a half base squared. It's 1/2 base height, right? So it's just a half. So number 4 is exactly the same answer as number 3, except it's a half out front. Okay? I'm going to shut this down.